So we're going to continue low latency memory today. Hopefully we'll finish it, but we'll see how much we can finish. Any questions so far from yesterday's lecture? Well, you'll have a lot of opportunity to ask today also, because we're going to cover similar topics. And this is what we're striving for. And hopefully I motivated that this is a good thing. I think ignoring latency is not very good in general. Okay. And we were looking at two major causes of latency and efficiency. So what's the problem I'm having with all these chargers today? So that means that we're consuming a lot of unnecessary energy. It's amazing. It seems like it's working. It indicates there are two out of third is charged, but it's not working really correctly. Okay, let's keep going. So basically we were looking at two major sources of latency inefficiency in modern DRAM, and one of them is due to the design of the DRAM microarchitecture, which is designed to minimize cost or maximize capacity per area, which is the same thing, not minimize latency. And we looked at one example of this, which is tiered latency DRAM. If you remember, this introduces heterogeneity inside the DRAM subarray, where you segment the bit lines with isolation transistors, such that part of the DRAM subarray can be accessed with low latency, yet you still have high capacity because the rest of the DRAM subarray can be still accessed. And there's very low cost because the only cost that you have is really the isolation transistors inside the DRAM chip. Okay, so you remember that one. I like this idea. I think it's a cool idea. It's one of the first works that try to reduce latency in DRAM without having a lot of cost. There are a lot of works that propose reducing latency in DRAM with a lot of cost. And we will see some of them. But if cost is a concern, you really need to think a little bit differently. Okay, I'm going to talk about another one. You can see that cost is also in the title over here. This is the goal of this is going to be motivated in some other way. But if you think about tiered latency DRAM, what it does is really it creates heterogeneity in DRAM, and does so by segmenting the bit line. Basically, it gives you some more controllability in terms of how your interconnect is configured, right? You don't have a single linear interconnect, but you can nearly partition your interconnect into two. When you turn on the isolation transistor, you have a long interconnect. When you turn off, you have a small portion that's really small. That's how you get low latency. Here, we're going to add more connectivity into the interconnect that we have in DRAM, and we're going to go into a little bit more detail in terms of the DRAM architecture. And I think going forward we really need approaches like this. If you look at our memory chips, I think I mentioned this before, if you look at our memory chips, they're not very well interconnected with each other. You have data all over the place, there are a lot of subarrays, but the interconnection is missing inside the chip. And I think this, if you look at a structure like brain, for example, there's a lot of connectivity in the brain. And I believe we're not doing the right things in the memory chips if we're actually trying to imitate what the brain looks like. Basically, we need to increase the connectivity in DRAM. But I'm going to motivate it in some other way. If you remember, bulk data movement is important, and we talked about that in row clone. And this paper actually was initially motivated to solve a problem that row clone has. If you remember, row clone is very good at doing row copy inside a subarray, within a single subarray. Row copy or any granularity copy between two banks is also okay in row clone. But if you want to move data between two subarrays in the same bank, row clone is really inefficient. In fact, it didn't gain any performance compared to doing this across the memory controller, if you remember. And this paper actually was initially motivated to solve that problem. And the problem is basically it's the same as row clone. If you want to copy the source page to this destination page across a memory channel that's not as wide as the page itself, you do a lot of unnecessary data movement, and this leads to high latency. And this is Kevin Chang's animation. He was my PhD student, and he was very good at doing animations, as you can see. Clearly, you could do this for 8 kilobytes, and that's going to take a long time. If animation takes a long time, real life also takes a long time, right? Okay, we're not going to do that. But clearly this has long latency and high energy. So if you want to move data inside DRAM, let's take a look at what row clone is not very good at. Basically, you have a single bank, and you have DRAM cells, it's the bank abstraction, and you have a bunch of subarrays inside a bank, let's say hundreds, in this case n. And you can see these are some parameters we mentioned before. And if you want to move data between subarrays, you need to go through this internal data bus. Basically, this subarray, if you want to access data from a subarray, you need to access the row and a column access brings you 64 bits out of the subarray, and then now you can access that data. But if you want to move data between two different subarrays, you have this low connectivity. There's no way to move 8 kilobits of data with a 64-bit bus in a relatively short time, right? That's the idea. You've seen this picture before, actually, when we talked about DRAM microarchitecture yesterday. So that's the observation in this paper. If you want to move data between two subarrays, you have very low connectivity between the subarrays. In fact, what you need to do is you need to take the data out of the subarray, 64-bit by 64-bit, move it to the outside of the subarray, somewhere inside the DRAM chip, and then move it back into the destination subarray. Right. Row clone solved this problem by moving this into moving an 8 kilobit row or a row into some other bank, a temporary row in some other bank through this internal data bus, and then moving that row from that bank to the destination subarray. Right. That's very slow. So we want to do something else. So can we do something else? The key idea is really to increase the connectivity. So we want to provide a new substrate to enable wide connectivity between subarrays. And once we realize this, that connectivity is the problem, the solution is relatively simple. And the solution is going to be relatively similar to the isolation transistors that we use inside the tiered latency DRAM. Basically, you have multiple subarrays. We want fast block data movement, so we connect the subarrays with each other via isolation transistors. In today's designs, these subarrays are not connected. The proposal is to have isolation transistors so that you can move data relatively quickly between this subarray and that subarray. Hopefully it's obvious, right? Now that you know about tiered latency DRAM. Now if you turn off these isolation transistors, subarrays operate independently. If you turn them on, then that means that you connect the bit line in this subarray to the bit line in this subarray. Then you can transfer the data from the row buffer of this subarray to the row buffer of this subarray. You could potentially transfer directly between the rows also, but this paper proposes transferring into the row buffers. And this turns out it's not good just for moving data between subarrays, but it enables multiple applications. Fast block data copy is one. You can see that original copy latency from one subarray to another subarray is on the millisecond level. It's very similar to doing it through the memory controller. But you can actually improve that by almost an order of magnitude, and that leads to significant speedups and reduction in DRAM energy with some applications that do a lot of copying. You can also do in-DRAM caching. I'll talk about this briefly. For example, you may have a subarray. If you recall, one way of reducing the latency is to reduce the bit line length of a subarray. So you may actually use an idea similar to tiered latency DRAM across subarrays. You can have heterogeneous subarrays. Some subarrays can be long bit line, some subarrays can be short bit line. Right? Imagine that. This subarray may have 1,000 rows hanging off the bit line. This subarray may have only 32, which means that fundamentally the subarray is faster, which means that you can use it as a cache again. Then the question becomes, how do you use it as a cache? You need to move some data from here to here if you want to do dynamic caching, and this substrate enables that movement of data, dynamic movement of data between subarrays. So that's the idea. So once you start thinking creatively, you can actually come up with a lot of good ideas. There's also another thing that this enables, which is interesting, which I will talk about. It turns out this can reduce the pre-charging latency. So pre-charge is, remember, the pre-charge operation prepares the bit lines for the next access, prepares the subarray for the next access by setting the voltage on the bit line to VDD over 2, to a reference voltage. And this takes time. If you remember, if you get a row conflict, you first need to pre-charge the array, which means that you kind of write the row back, which is equivalent to setting the bit lines to VDD over 2, and that takes a long time, and that's on the critical path of accessing the subarray in a different row. And it turns out you can actually reduce the pre-charge latency by actually using the pre-charge driver circuits of two adjacent subarrays at the same time, because now subarrays are connected to each other. You will see this more clearly in a little bit. So basically, I think this is an example of adding more connectivity enables a lot of interesting things inside the DRAM. If you didn't have this connectivity, then you wouldn't really be able to do any of these, at least across subarrays. Okay, so let's take a look at how this works in a little bit more detail. Basically, this is a new command that you need to use to enable Lisa. It's called row buffer movement. It moves a row of data to an activated row buffer, in an activated row buffer to a pre-charged one. Let's take a look at how this works. Let's assume that we want to move data from this subarray to this subarray, and these are the sense amplifiers. We actually divide this into sensing logic and pre-charge logic. So you can think of this as a row buffer. If you remember, row buffer and the sense amplifier is the same thing. It's used interchangeably. So these are the sense amplifiers or the row buffer of subarray 1. These are the sense amplifiers and the row buffer of subarray 2. And these are the isolation transistors that we add. So let's assume that we want to activate some row over here and move it to subarray 2. How do we do that? We first activate the row that we want in this first subarray. Now the data of the row is inside the sense amplifiers and it's activated. This subarray doesn't have anything inside it because we didn't activate it. Now if we want to move this, okay, this is a bit annoying. Now it decided it's not going to work with me. Oh, maybe it's working. Okay, so if you want to move, let's do it this way. If you want to move that thing, oh, that's not going to work also. Okay. Maybe I'll give this to Juan and he can fix it while I'm doing this. Thanks. There are extra batteries over there. But I think there's something wrong with that device itself. It's not a battery problem, I think. Okay, so if you want to move that activated row buffer to the pre-charged one, we enable a row buffer movement command from subarray 1 to subarray 2. So the memory controller can actually issue this command, which turns the transistors, isolation transistors on, which means that the I cannot see anything here. Today we're having a lot of technical issues. Okay, this is much better. Okay, which means that now you can connect this row buffer to this row buffer. And how do you do that? Basically by charge sharing, right? You can see that these are all charged on top, and this bit line is pre-charged, which is VDD over 2, which means that by charge sharing through the row buffer, you can essentially move the data that's in the top row buffer to the bottom row buffer. Make sense? It's the same procedure as if you were activating a row over here, except there's already something activated over there. And once you turn on the isolation transistor, there's charge sharing that happens, and that kicks in, triggers a sense amplifier to amplify the charge, and everything becomes the same value as this one. Make sense? So it's just like you were activating a row, except you're doing an activation across row buffers. Did it work, you think?
I think so.
Okay, thanks a lot. Yeah. But this is really consuming battery much faster than it is supposed to. Okay, so hopefully that's clear. Okay, clearly adjacent subarrays are connected this way, right? And this transfers an entire row between adjacent subarrays. Of course, you could imagine doing this more, right? You could do it. You could have another subarray over here. If you want to transfer data from subarray 1 to subarray 3, maybe you enable isolation transistors here as well as here, right? But of course, that takes longer latency now because the interconnect becomes longer, right? The charge sharing takes longer to ensure this data over here gets copied all the way here. Make sense? Yes?
Is it also copied to the subarray 2 as well? If you're trying to copy from 1 to 3, so is it automatically copied to 2 as well?
So yes, exactly. That's a good point.
What was the question?
Basically, if you have subarray 3 over here, as I described, if you're copying from 1 to 3, is it also copied to 2? And the answer is yes. You'll need to do that. Yeah. Unless you provide some other path, of course, which we don't. Yeah.
You also have to pre-charge subarray 2 and 3?
Exactly. You need, basically, this needs to be pre-charged. If there's something that's already activated over here, and if you do that, then you don't know what the value will be, right? Because this is not in reference voltage at that point in time. Okay. And of course, the memory controller needs to control all of that, right? Okay, basically the range of this row buffer movement command depends on the DRAM design clearly. In our design, basically we say if you want to move data across more than 3 subarrays, you need to use multiple row buffer movement commands. Right? If you have 128 subarrays, for example, if you want to move data from the top subarray to the bottom subarray, you do row buffer movement 1, 2, 3, 4, 5, n number of times such that eventually the row gets to the bottom subarray. This takes time, of course, because you don't have complete connectivity across subarrays, right? This is basically a limitation of the interconnect. Interconnect is connected. This is really a daisy chain interconnect in the end, right? This is called a daisy chain. Only the adjacent subarrays are connected to each other. We will see later interconnects You could say this is a ring, but it's not a ring really. A ring really connects all of the subarrays and completes a loop. The difference between a daisy chain and a ring is daisy chain is really not connected on the edges. Right? So if you want to go from one subarray 1 to 128, you really go through 128 hops. Okay, so basically this is the example that I mentioned. If you want to copy data from subarray 1 to subarray 3, you can do it this way. And as you mentioned, it also copies data over here. And you should make sure that both of these are pre-charged. And if you look at the paper, there's validation that's done, and there's a lot of simulation that's done in circuits. And if you add some guard band, which we're going to try to remove in the next part of the lecture, you can get significant bandwidth. Basically, you can do this copying at 500 gigabytes per second, which is about 26 times the bandwidth of a memory channel itself. Okay, so basically you can get high bandwidth, low latency copying. And the area overhead is relatively small according to some calculations. Okay, so let's see how we can use this. Basically, clearly you can use this for copying a row efficiently across subarrays. You use RBM to form a new command sequence for that purpose. And I've already given you, I think. You first activate the source row, which brings the data into the sense amplifiers of subarray 1. And then you do RBM, which basically takes the data from subarray 1's row buffer and puts it into subarray 2, pre-charged subarray 2's row buffer. And then, if you want to copy the data into some other row over there, you just activate the destination row. You don't necessarily have to do that, right? This is one way of copying. You may actually want to use this row buffer for some purpose, right? Basically, if you don't want to copy the data over here, you may directly access the data from this row buffer. Make sense? Okay. As architects, you can imagine a lot of things. And it turns out this reduces row copy latency significantly, and also row copy DRAM energy significantly. It's not as much as doing it inside a single subarray, clearly, but it's still very close. If you remember row clone, doing it inside the subarray was about 11x, and it was reducing the DRAM energy by 77x. This is slightly smaller, but it's still quite good. Okay, so let's take a look at some other applications of this. So if you want to actually reduce DRAM latency with low area overhead, this is a caching application. It's called variable latency DRAM. Clearly we have a trade-off between area and latency, which we already discussed. This is a long bit line architecture. This is a short bit line architecture. It has a lot of area overhead, which is not really depicted well here. And you already know that if you have shorter bit lines, you can have faster activation and faster pre-charging. Things become faster. But if you have actually shorter bit lines, this paper does a lot of analysis and shows that if you actually reduce the size of length of your bit lines, you get significant area overhead, 40%. We don't want that area overhead. We want to get the benefits of short bit lines with less area overhead. Basically, we want to reduce the access latency of hot data via heterogeneous DRAM design. And tiered latency DRAM gives you one sort of heterogeneous DRAM design by adding heterogeneity inside a subarray. And there's another way of introducing heterogeneity by having heterogeneous subarrays. Basically, you can add fast subarrays as a cache in each bank. And this is the idea, basically. Your internal DRAM architecture looks like this. Maybe a lot of your subarrays are relatively slow and large, but some of them are fast. Right? This is kind of similar to the tiered latency DRAM substrate, but you don't change the subarray itself. You don't change the subarray structure itself here. You don't have isolation transistors inside the bit lines. You have isolation transistors across the subarray boundaries, like what we discussed. Now you can use this as a substrate for caching hot data, and you can do this profile-based mapping. But if you want to dynamically migrate data from a slow subarray to fast subarray, such that you can access it faster, we use the isolation transistors. Right? Basically, this requires frequent movement of data rows if you want to do dynamic caching. And LISA, low-cost interlinked subarrays, enables that dynamic data movement rapidly from a slow subarray to fast subarray with the same mechanism that I just described. Right? You enable the isolation transistors over here, or you enable the isolation transistors over here to move the data this way. You can go both ways. Actually, it's a bidirectional daisy chain that way. Okay. And it turns out this significantly reduced the latency of hot data access with relatively small area overhead. But you can read the paper for more detail over here. Any questions? Okay. Okay, the last one is also interesting. Basically, once you have more connectivity, you can do other interesting things. These were not envisioned when Kevin was first developing the idea, basically. The goal was really to reduce the shortcoming of row clone when you actually copy data across subarrays within the same bank. But it turns out you can do other things once you have connectivity between subarrays. And one of the things that limits latency in DRAM is pre-charging, as I said. In conventional DRAM, whenever you want to turn off a row, so that you can activate some other row in a subarray, you need to pre-charge the subarray, which means that there's some unit over here, which we didn't talk about so far, but there has to be some unit close to the row buffer. It's called a pre-charge unit that essentially goes and sets the bit line to VDD over 2. That's the idea. It's called a pre-charge unit. We're not going to go into the details of how it does it, but it does it. So pre-charge unit needs to be on, and it has some latency to set the subarray to set the bit lines to VDD over 2. Now, the key idea with Lisa is to use multiple pre-charge units to make this pre-charging faster. In the baseline, you have a single pre-charge unit that can pre-charge a subarray, but if you actually connect this pre-charge unit to this subarray, you can pre-charge on both ends. That's the idea, basically. You turn on the isolation transistors, which means that these pre-charge units on top get connected to this subarray. Now, if you want to pre-charge this subarray, you turn on both of these pre-charge units, and there's a pre-charge command that the memory controller sends. That's what it turns on. And this is called link pre-charging. Basically, both pre-charge units start pre-charging, and you reach VDD over 2 much faster that way. And according to circuit simulations, you can actually reduce the pre-charge latency significantly, as you can see over here, even while keeping some of the guard bands. We will talk about those guard bands a little bit. Guard band is basically margin that you add to the latency. Your real latencies are actually much lower, but you add some margin because you don't know how the circuit will change depending on temperature and depending on aging. Right? Over time, your latencies may increase, so you actually say, my latency is actually higher than what I really can access memory with. Does that make sense? Okay, this is going to become more clear. So any questions? I think this is the beauty of adding more connectivity to memory. In general, connectivity is good. And if you're interested, you can take a look at this paper. I'm not sure if I will assign this yet. But I wanted to give you the idea of connectivity in memory. I think there's more to be done. Frankly, there's actually some other work that people are looking into adding more connectivity inside memory. And those are, if people figure out how to add that connectivity really well inside memory, I think that's going to be the real AI chip, if you will. People are really trying to design these machine learning chips today. But they're either limited by memory or computation today. Most of them are limited by memory. But once you start doing computation in memory, you'll be limited by the connectivity that you have inside the chip. Because in the end, you'll have to move data somewhere. You cannot just operate on a small subarray. And to enable fast data movement, you really need to have more connectivity. That's why I mentioned when we talked about memory problem early on, is the problem with memory or is the problem with interconnect? It's really a problem with both. And in the end, it's really a problem with communication. Right? Data movement is a communication problem. And communication problems can be solved by more connectivity and more interconnect. Okay. Any questions? Okay, so let me move on. This is, I think there will be a longer talk about this later on, but we've been working on reducing latency, and this is one of the latest substrates to reduce latency, as well as do other things. But Hassan will give a talk about this later on during the lectures. So I'm not going to go into a lot of detail over here. But this idea actually reduces the cost even more. So basically, we want to reduce access latency, we want to reduce refresh overhead, and we want to handle issues like row hammer at the same time. The question is, can you design a substrate that can handle a lot of them at the same time? So if you look at conventional DRAM, you've already seen this many times. You basically have this sort of structure, and you activate the row, which brings data into the sense amplifiers. So the Crow substrate proposes something kind of similar to tiered latency DRAM, but it gets rid of the isolation transistors. Basically, those isolation transistors add cost. In this case, we don't want to add that cost, but it's going to take advantage of something different. So this kind of looks like tiered latency DRAM, right? You have two parts. this part, let's call them copy rows, and you have this part, let's call them regular rows. Now we're not going to talk about near segment, far segment here because there's no isolation transistor, but we're going to use this substrate in a different way. And you have two kinds of decoders. So this is definitely much smaller. It's 1 to 8 rows. And this is, let's say, 512 minus 1 or 512 minus 8 rows. Okay? So how can you use a substrate like this when you have two decoders? Let's take a look. Basically, you can enable a row copy using row clone. We know that already. There's nothing new here. Basically, you activate the source row, which brings data into sense amplifiers, and then you activate the destination row over here, which means that you copy the content of this row into this row. Okay? Now the question is, can you access this row faster? Tiered latency DRAM enables access to that row faster by isolating or segmenting the bit lines and isolating this part. So we're going to enable access to that row faster by doing something else. So by doing multiple row activation. So the idea is, if the same data exists in this row and also this row, if you activate both of them at the same time, chart sharing is much faster, right? Because you have two cells really driving the bit lines, and it turns out, according to circuit simulations, chart sharing becomes faster, sense amplifiers become enabled faster, and this multiple row activation at the same time reduces the latency of activation. Do you have a question? No? Okay. I thought you were raising your hand. Fine. So that's the idea over here. Does that make sense? So it's amazing what you can do if you think a little bit out of the box, right? The current thinking is you can only activate one row, but if you think a little bit out of the box, say we want to activate multiple rows, and they both have the same data, the access to that data is now much faster. Okay. So there are many use cases of this. One is you can use this as a cache. So if you go back over here in this picture, this part is kind of a cache of frequently accessed rows. And whenever you access a row, you basically copy it over here. And whenever you need to access the same row again, if it's in the cache, you activate both the original data and the cache data such that you access it much faster. So the latency reduction comes from the fact that you're activating both rows with the same data at the same time. Okay? So that's one use case. Clearly that reduces access latency. I guess there's animation over here. You basically activate this row, you copy it over here, and then the next time you access the same row, you basically do multiple activation in this part and then this part because you have separate decoders for them. Okay. You can also reduce the DRAM refresh overhead by somehow identifying these weak rows and then disabling them. This requires clearly identification of weak rows. Weak rows mean the rows that have weak cells that cannot retain data for longer. Let's assume that you identify this to be a weak row. In the memory controller, you remap it to a strong row over here. Meaning you need to have a mapping table saying if you access this weak row, don't access this part, access where it's remapped. That requires a little bit more overhead clearly in the memory controller. And also it requires the identification of what's a weak row, which we talked about when we talked about refresh. Although we didn't go into a lot of detail on how to exactly identify it, we talked a lot about the challenges of identifying it. But this substrate enables remapping of a weak row to a strong row, and that reduces the refresh overhead because now you can actually find all of the weak rows in your DRAM, and there are not that many weak rows if you remember, and you can remap them to strong rows inside this portion of DRAM, and that way you can reduce the refresh rate. And according to the paper, there's actually a significant benefit from this, and the paper has some analysis. You can take a look at it. The paper also briefly talks about this could be used as a mechanism for protecting against row hammer, and the way you can do it is by using this mapping functionality. Basically, you somehow figure out which rows are being activated frequently. And there are mechanisms that are being developed to do that with low overhead. If you figure that out, what you can do is you can map the data of this row to a row over here using row clone, right? That way you can actually protect whatever used to be a victim rows over here if you do that quickly enough. Does that make sense? Basically for this, of course, you need to figure out which rows are being accessed very frequently. Okay, So let me give you some key results from the paper. So this actually, you can combine these also at the same time, right? You can actually have all of them at the same time, assuming you have enough of these copy rows at the bottom of the subarray. And if you combine this caching mechanism and refresh reduction mechanism, you get significant speed ups and energy reduction across a number of applications. And you can see that the hardware overhead is relatively small. Tiered latency DRAM requires about 3% DRAM chip area overhead. This requires about 0.5% DRAM chip area overhead. You lose some capacity, clearly, because you cannot use those copy rows for something else. You could potentially if you're not doing this, of course, right? But you lose some capacity, and memory control needs to be modified also, as you can see. But the overhead of this is relatively low, and this is really one of the state-of-the-art works in latency reduction. And the paper has a lot of comparison to tiered latency DRAM if you're interested in reading it. Okay. And that's the paper. Any questions? I wanted to give you these examples because these are all examples of a mindset change, if I should put it that way. The mindset is really not I designed the DRAM for low cost. The mindset is I want to keep low cost as much as possible, but I really want to reduce latency. Right? And once you start thinking that way, the ideas, in my opinion, are endless, really. I don't believe this is the end of low latency DRAM. I believe there are more ideas to be discovered, actually, in this direction. And if you're really interested, you could actually play with the source code as well. Okay. So let me, any questions? Is it boring? No? I don't, yeah.
One basic thing, like when we are activating both the rows, why the latency is reducing? Because when we are activating the nearer rows, then I can understand that the data is moving faster to the sense amplifier, but still the latency is still there on the like whatever is the distance there is. Yeah. So maybe the voltage we are like the charge we are getting, maybe it's more, but how it is reducing the latency?
So exactly because the charge is more. So what happens is when you have more charge that's being shared with the bit line, the bit line gets perturbed much quickly, and the sense amplifier gets activated much more quickly. That's the main reason. Okay. I will later show you some curves related to that, but that's, yeah.
It's like sense amplifier is taking very less time in order to decide whether it's a one or
Exactly. That's what's happening. There are multiple things. You first more quickly activate the sense amplifier, and the sense amplifier actually takes less time as well.
So is it like a dual port RAM where we have like two ports which we can consider top, like one port is the top one and the second one is the one that is having?
I mean, it's not exactly that way because we're not getting multiple data elements. We're still getting a single data element, right? We're not increasing the ports in the DRAM. But within a subarray, if you think about the subarray abstraction, yes, within a subarray you can access two things at the same time. Except latency reduction happens when two things are exactly the same data.
And is it not the time taken from the top row to the sense amplifier, and there would be a difference between the time the charge is coming to the sense amplifier?
So there's certainly that difference, but that's already accounted for in all of the experiments. So in the circuit modeling, that's already accounted for. You mentioned that yesterday also. There's certainly a difference, and we will see that more. Any other thoughts? Now you're ready to design the next big low latency DRAM? Okay. So this is the state of the art. But let me also tell you the thing that really started all of this. This is actually the first paper that we've written in this area. So if you look at this stuff, if you look at LISA, for example, LISA assumes that you can really activate multiple subarrays at the same time, right? But that's when we first started, that was a big no-no also. People didn't activate the multiple subarrays. But we thought that this was a good idea, actually. And this paper kind of introduced the idea of activating multiple subarrays at the same time at low cost, again. So let me talk about the problem. So the problem, we talked about bank conflicts yesterday. You have multiple banks in DRAM, but if the access is mapped to the same bank, you have a bank conflict. Basically, you need to activate row A, and then you need to activate row B, which means that you have a row conflict, right? Row conflict is the same as a bank conflict, actually. And these are costly for performance and energy, clearly. And if you're actually doing this repeatedly, AB, 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 that's really bad. It really serializes your requests. It wastes energy because the row buffer gets trashed. You have a single row buffer, right, in the same bank. And you get busy waiting, basically, because it's not just activate, right? You activate, you read, and then you have to pre-charge the array so that you can do the next activate. Right? So it's actually about 55 nanoseconds in total, ignoring the reads. If you don't do any read to a row, the row cycling delay of DRAM is about 55 nanoseconds on average, let's say. So this is not good in general. And a lot of the ideas that we've discussed are actually dealing with these bank conflicts. Remember when we talked about TL-DRAM yesterday, the benefit of caching at that level is really dealing with bank conflicts. That's true for CRO also, actually. CRO is really reducing latency for bank conflicts. And when we first started, we thought this is a bad thing, so we should reduce the latency of bank conflicts as much as possible, but without adding more banks. Of course, one solution is to add more banks. But adding more banks is actually very costly. I think I will show you some results in terms of the area overhead. It's significant, very significant. It goes up to, depending on how many banks you want to add, of course, it could go 2x, 3x area. Because once you add more banks, you're really adding more row decoders, and row decoders are very big. Okay, so the observation in this work is what is kind of obvious to you right now, because we started with the newest works in a sense. A DRAM bank is divided into subarrays, and each subarray has its own local row buffer. So basically, logically, the bank looks like this, but physically, it really looks like this. Let's assume that you have 64 subarrays in this case. Each of the subarrays, this may be 32,000. Here, it's really 512, right? And each subarray has its own local row buffer. Make sense? And whenever you're really activating a row, you're really activating a row in a subarray, and you're bringing the data into this local row buffer. So why is it done this way? The reason is, if you had 32,000 rows in a single bit line, the latency would be even worse. Much, much worse than today, actually. So DRAM manufacturers actually don't do that, because that's really bad. They actually make the subarray 512 rows. The latency becomes much shorter to activate a row. But it's still long, as you can see from the processor's perspective, because that interconnect is still long. But now you have multiple subarrays over here, and only one of them is active whenever you activate a row. So the idea in this paper is, can we take advantage of the fact that you have multiple subarrays to reduce the latency of bank conflicts? So when you get a bank conflict, what happens is, let's assume that row A is here and row B is here. Row A is in subarray 64, row B is in subarray 1. If you keep repeatedly accessing row A and row B, what happens is, you activate row A, you bring the data into the local row buffer, you send a read command which brings the data, 64 bits, to the global row buffer, and then you're done with the read. And then you need to access row B, which means that you need to pre-charge the subarray, and then you need to activate row B over here, which brings the data into the local row buffer over here, and then you send a read command, you read the 64 bits, and then you keep repeating doing the same thing over and over. So that's a lot of overhead, even though they may actually internally map to different subarrays, right? The idea of this paper is exactly that. If two consecutive accesses map to different subarrays, why don't we take advantage of the fact that their local row buffer is over here and have multiple subarrays activated and pipeline the requests? That's the idea, basically. Okay, so basically this requires exposure of the subarrays to the memory controller. So let me go over the key ideas. And the second idea is basically, how do you do that? So assuming that now you realize that multiple subarrays exist, and you can potentially access them almost concurrently. You first activate this one, and then you maybe activate that one. Now you can overlap the latencies. But then how do you do that with low overhead? One of the options is clearly making each of this a bank, right? Having completely independent subarrays, which essentially makes it a bank, which really reduces your bank size. But now the overhead of that is very large, because you need to have a complete row decoder over here, here, here. You need to have 64 row decoders in this picture where you have 64 subarrays. Okay? So that's not good. We really want to have minimal cost while enabling maximal parallelism across the subarrays. And the second observation enables that, basically. It turns out subarrays are mostly independent internally. So if you go into a little bit lower level of abstraction and the design of the subarrays itself, this is what it looks like. You have a single global decoder. When you get a row address, it gets decoded and a word line in one subarray is activated. because you have a single global decoder that decodes the address, row address. And then you have a single global row buffer. What happens is, whenever a row is activated, the bit lines, whenever you do a read from an activated row in a subarray, all subarrays get connected to the global row buffer, because it's a single bit line over here. It's a global bit line, it's a long bit line. But only one of them drives the global row buffer, because none of them, other than the one that's activated, is activated. Right? Everything else is idle. So this is going to become more clear. Basically, they're mostly independent, except you have these global structures that are shared to reduce cost. You don't want to have completely separate decoders here. You have a single global decoder over here. So the key idea of SELP, Subarray-level parallelism, is to minimally reduce sharing of these global structures such that you can enable maximal amount of parallelism across the subarrays. So how do you do that? You want to reduce the sharing of the global decoder, somehow enable activation of different subarrays in consecutive cycles. We're going to see that. And you should reduce the sharing of the global row buffer such that if you have two activated subarrays, only one of them can drive the data out of the chip or out into the global row buffer. Because if you have both of them drive, that's not a good idea, clearly, right? Okay, so we're going to see how to do that. So this proposes a low-cost mechanism to do that. Let's take a look at two subarrays over here. Let's assume that this is row A and this is row B, and we're kind of ping-ponging between them. Now, in the baseline design, you have this global decoder, and you get the address. The address gets latched over here, and a single row address gets decoded. Clearly, let's assume that the address is A. The address activates this blue part, right? Now, what we're going to do is we're going to push those latches to be here, as opposed to a global latch. It's a very simple modification, right? Have a local latch per subarray latch as opposed to a global latch. What this enables you to do is to get the first address, row A, latch it over here, and now you can drive this one, activate it, and which brings the data over here. In the next cycle, you get the row address B and latch it over here. Now it can independently drive this subarray's word lines. It selects a single word line, the subarray's decoder, and then you can activate row B at the same time, almost at the same time. You have to do it in consecutive cycles, clearly, right? Because you cannot send two addresses at the same time. You could modify the DRAM interface to do that also, but we don't want to do that in this case. So we're sending row A in the first cycle, it gets latched, you activate, which brings the data into the local row buffer. In the next cycle, well, of course that takes a long time, right? Latching takes a single cycle, but the activation itself takes a long time. While that activation is started, in the next cycle, row B's address gets latched and decoded, and row B gets activated, and both of the activations happen in parallel. So basically we're hiding the latency of row B's activation while row A's activation is going, by exploiting the parallelism. That's why it's called Subarray-level parallelism. Right. Okay. It's a cute idea, I think, with very simple changes. Okay. So basically this is one. But you need to do something else also, because this is actually changing the picture a little bit. We wanted to basically have global bit lines over here, right? And those global bit lines directly get connected to the local row buffers. For example, if you want to do a read from this subarray, the data gets directly connected to the local row buffer, from the local row buffer to the global bit line. And the connections are not configurable, meaning that whenever you do a read, this gets connected as well as this gets connected to the global bit line. You don't want that. You want to have some configurability. And that's the idea over here. You want to be able to selectively connect a local row buffer to a global row buffer, which is the I/O, using the selective connectivity circuit. It's called a designated single bit latch. Let me give you the idea. Basically, actually there should be another animation over here. If you do a read, today you don't have that switch. Basically, the local buffer directly gets connected to the global bit lines, but today you have only one activated subarray. That's okay. Even though this is directly connected, it doesn't matter because there's no charge over here, right? But this gets connected and it can drive the global bit lines, right? But if you have two activated subarrays with two row buffers that are charged, now if you do that, if you read and if you don't have a switch over here, they both get connected to the global bit lines and you get garbage value. You get a short circuit actually, right? We don't want that. If you want to not have that, which you should not have that, then you actually selectively activate, selectively connect a row buffer to a global bit line. So the way you do it is basically we add a single bit over here. It designates the subarray for reading. And if you want to send a read command to, let's say, this row A over here to the blue subarray, what this does is it connects this subarray to the global bit lines, and you get the data out of the chip. Of course, this is under the control of the memory controller. If the memory controller wants to read something from row B, what it does is it disconnects row A subarray, and then it connects row B subarray, and then it gets the data out of the global row buffer. This is minimal modification clearly, right? We don't want to add different read paths, because once you start adding different read paths over here, it becomes completely different banks. Right? But we want to preserve as much as possible in the existing microarchitecture so that you can mostly parallelize the activates, and you can use the row buffers in different subarrays without adding a lot of cost. Does that make sense? Okay, I see you had like this. Okay, and this of course requires some more logic and area with these designated bits, and this is actually a little bit more additional cost in the DRAM chip. But it's not as bad as making these completely different banks. So what this now enables is really you can have two activated rows in a single subarray. So imagine you're actually doing row A and row B. They're both activated over here. You're not going to do additional activations or pre-charges. You just need to switch between these designated latches. Right? That's the only overhead that you have now. So basically this is, I think this is the baseline bank organization in the end, and this is what we end up with. So the difference is relatively small, as you can see. And according to our calculations, it's about 1% area overhead. We were actually this is what we underestimated, I think, in our earlier works. I think 0.15% is actually a little bit too low for this change. But over time, you also the downside of doing research in this area is it's very hard to get real numbers in DRAM chips. Nobody publishes them, and whatever is published is actually relatively old data. So I believe the overhead of this is actually a little bit higher than this one, but it's not as high as many things. And I believe you can actually hide it if you really design it very carefully. Okay, so let's take a look at the results, I guess. So in the paper there, yes, please.
Just if we saw, as we saw from the previous example, a result can come at a very different time. So maybe the yellow could come way before the blue.
That's correct, yes. Uh-huh.
And so, but the person who is saying who can store in the global row buffer doesn't know which one arrived first, right? Oh
no! So basically, the result can come. It's all dictated by timing parameters. So the memory controller issues an activate. It knows that the result will be available after some time. It's after a fixed time.
But we saw that it could be not a fixed time.
Which one cannot be a fixed time?
So, for example, if we store something that is very far in the yellow array, it can take a lot of time, and that is very close. So that is true, yes, but we're not doing that. Basically, whenever we access the subarray, there's a fixed latency so that the memory controller knows. The one where we... Exactly, we forget about that part. Yes, absolutely. So that was a different idea. Basically, we're not exploiting any other timing here. If you actually exploit that, then you need to have a different protocol for sure. So now we assume that it's constant time. Exactly. We assume each subarray access latency is constant time. And the memory controller knows that, and it ensures that there's no conflict over here. Makes sense, right? Now, if you want to combine the many ideas that we've discussed, then it becomes really interesting, of course, right? But then benefits also need to be evaluated. Okay, so let's take a look at the results. Remember, this work is done in 2012. It was published in 2012. Everything else I've discussed is after this. I just want to give you the history of this a little bit. So this paper actually analyzes a lot of workloads, and it basically shows that you can reduce the DRAM energy significantly by increasing the DRAM row buffer hit rate, because you're not actually getting row buffer conflicts anymore, because you're enabling multiple subarrays. And this also leads to significant system performance improvement.
you can see that it's about 17%. It's within 3% of the ideal. Ideal means instead of making the subarrays mostly parallel using subarray-level parallelism, you really make those subarrays independent banks. That's really the ideal or upper bound of this mechanism. And you can see that it's significant, but this is the area overhead of making all of those subarrays banks, complete banks. That's about 36%, which is a lot. And there are a bunch of different lower overhead versions of subarray-level parallelism that buy you less performance with even less area overhead. And you can read the paper for those. Okay, and we've already discussed this. Any questions? Okay, so these ideas are definitely combinable, as you kind of alluded to. Like this, on top of this, you can add the isolation transits of Lisa without any additional. Of course, memory scheduler needs to be careful, right? The burden is on the memory controller to schedule the requests, and we have not even talked about that. How do you schedule the request becomes a little bit more complicated if you have a lot of subarrays like this. But for example, let me give you an example where you get really bad bank conflicts. Let's assume that you're streaming through two arrays, array A and array B, and you're adding these two arrays somehow, and unfortunately they may happen to be mapped to the same subarray. That's not good, right? or same bank. In the baseline, they may happen to be mapped to A may be here, B may be here, right? Now, in the baseline, you get bank conflicts, and you're really streaming through memory. In subarray-level parallelism, it's mostly okay, right? Basically, you don't need to get the bank conflicts. You just need to switch between these designated latches, and you don't pay that overhead for a long time. Now, of course, you don't get rid of all of the bank conflicts this way, because if A and B actually get mapped to the same subarray, you're back to square one, right? It's again a full bank conflict that you need to pay. So this points to the importance of data mapping. If you know your access patterns, it's best to map your data to different banks to begin with. And if you cannot map them to different banks, at least to different subarrays if you have subarray-level parallels. Okay. Okay. Actually, I think this idea is actually very useful for graphics workloads where you do a lot of streaming across many different types of, across many different parts of the screen, let's say. As long as you map your different parts, you get a lot of bank conflicts actually in those cases if your data is not mapped right. And if you map your data to different subarrays, you can actually stream through different subarrays relatively quickly. The only overhead being this designated latch switching. Okay. So this paper actually didn't evaluate those workloads. I think the benefits could be even higher. Okay, if you're interested, there's more in this paper. Now, let me tell you a little bit more about the history of this. So this is actually a relatively simple idea, I think. And this also tells you even simple ideas may not be easily accepted to begin with. These two companies who wrote this paper, Samsung and Intel, I believe that they're two of the most powerful companies in the semiconductor industry. And these two companies actually independently evaluated this idea in this paper. Basically, this paper, if you read it, it talks about a lot of things in DRAM scaling. And it talks about one of the things as increasing latencies. You have write latencies increasing, and this actually degrades performance. They talk about that. And they basically talk about our work saying that subarray-level parallelism is a good way of overcoming these increased latencies in the same bank. So the reason write latency is not good is what happens is you write to a bank and your write latency is long. There's something called write recovery in DRAM. Basically your bit lines need to stabilize, and it takes a long time for that stabilization to happen so that the data gets stored in DRAM. And these folks say that that's not good for performance in future technologies. Now if you're writing to one subarray, you can actually start reading from some other subarray if you actually have enabled the idea of subarray-level parallelism. That's the idea. And they evaluate this idea on their own, and they see significant performance benefits. You can read the paper in more detail. It's a bit hard to read some of this. But basically they show that you can compensate for the performance loss because of increased write latencies, but also even improve the performance when you apply subarray-level parallelism. Even if you increase the write latencies by 3x, according to their results. which is, I think, interesting. And they didn't even use the most aggressive form of Subarray-level parallelism, by the way. They used the relatively less aggressive form of Subarray-level parallelism, which is not as aggressive as what I described. Okay, so the story is these two companies actually tried to push this idea into a DRAM standard, and regardless of however powerful they are, they failed. So it didn't go into the DDR4, or I'm not sure about DDR5 right now, it's being discussed, but it definitely didn't go into DDR4 where they tried to push into. I think this is really a mindset issue. There's a lot of mindset and politics that's really involved in designing a standard. For example, you get a lot of these companies that decide what should go into the standard, and once you have something like that, a lot of non-technical concerns come in also, which is very interesting actually. I believe some folks thought that this introduced a lot of overhead in the memory controller, which I don't agree with. It doesn't really introduce that much overhead. And also, whenever you see overhead, the question should be, what are you getting for that overhead, right? If you were getting 0% for that overhead, sure, maybe that's not a good idea. But if you're getting something significant, like getting rid of a lot of bank conflict overhead, that may be a good idea. But this is an example of a research that had a lot of high impact because it enabled a lot of research. Clearly, these two companies found it very, very good to push through, but even then, it didn't happen. I think this is there's another thing over here that's also important. If you're in an industry that's really stuck with standards, that may not be a good thing. Because sometimes these standard bodies really are not good for innovation. If you weren't bound by the standards, what you could do is, look, I'm going to implement this, right? I don't care what the standard says. I'm just going to implement this idea and someone will pick it up. Now I think more companies should be doing that, really. That's exactly what UPMEM is doing, for example. They're trying to build a chip that completely disregards the standards so that you can actually enable computation. But this is an example of these standards actually leading to less innovation in the world. That's why I think these disruptive companies, I think Samsung and Intel actually could have done it themselves, but I don't know why they had to go through the standards route. I'm sure there are some political concerns also related to that. But if you want to get your idea out, try not to be bound by standards as much. That's another mindset issue. Any questions? Okay. So I believe this idea is actually eventually going to be implemented. It's just delayed because of the standards. Because this is something that just makes sense, in my opinion. It's relatively easy to do. It just requires people to get used to it, like many other ideas, right? Okay. And once you start thinking about the chip as not just banks, but other underlying structures, now you can enable other things inside the subarrays, like we discussed earlier. Is it a good time to take a break? I think it's a good time, actually, because we're going to switch to this next part of reducing latency. So let's take a break for 15 minutes and be back at 2:30. Okay, so let's start with the second way of reducing memory latency. And as I mentioned, this is another mindset issue, which is we're thinking of latency as a homogeneous thing where you have a set where you have a single set of timing parameters that's used regardless of the chip, conditions, and all of these things over here. Now we're going to break that mindset. By the way, feel free to finish it. If there's left, I don't need to take it back. Okay, I call this tackling the fixed latency mindset. And basically the key observation is that reliable operation latency is actually very heterogeneous across temperatures, chips, parts of a chip, voltage levels. And the idea, the overarching idea is this. Can we somehow find out and use the lowest latency one can reliably access a memory location with? And can we do it dynamically, of course? Initially, we're not even going to do it dynamically, but I think the best way of exploiting this will be doing it dynamically while the system is in operation, because now you can adapt to dynamic conditions very well, right? And we're going to see a bunch of ideas over here. One is adaptive latency DRAM, the other is flexible latency DRAM, and we're going to go into a lot of interesting ideas, trading off between voltage and latency, for example, with Voltron. And then we're going to see other things. Once you start thinking about latency as not heterogeneous, not homogeneous, a single thing, but heterogeneous, you reduce the latency and you start getting some errors, and you can use that to identify DRAM devices. Basically have a physically unclonable function. And you can also use that to generate true random numbers in DRAM. It's actually very interesting, I think. And it all comes from the mindset that we can mess with the latency, basically. When you mess with the latency, you start getting some errors. In this case, we don't want those errors. Here, we want those errors. And some of those errors are random. Some of those cells fail randomly. And this is a really true random number generator that you can build into DRAM. Let's see if we can get to that also. So basically, the goal here is really not to reduce latency anymore, but take advantage of the effects of reducing latency very aggressively to do something else. And maybe there's something else that happens after that, right? Basically, the key thing that we're going to try to do is we would like to find sources of latency heterogeneity and exploit them to minimize the latency or create some other benefits. Initially, the goal was to minimize latency, but once you start understanding what happens when you reduce latency, you can generate random numbers also. Okay, so let's see where this latency variation comes from in DRAM chips. And you've already seen this, right? It's basically process variation. Process variation leads to different retention times. Process variation also leads to different latencies. Basically, you get latency variation in timing parameters. Some DRAM has to be operated at high latency because it doesn't have cells that can be accessed with low latency, but some other DRAM can be accessed with very low latency. And there's variation across chips, and there's also variation within a chip, as you can see. Right? So within a chip, you have some slow cells and also some fast cells. Right? And this basically shows the reliable operation latency that you have to access the cell with. It's high here, it's low here. Okay. So, of course, the question is, why is latency high, right? DRAM latency is the delay that's specified in the DRAM standards. Basically, you take a DRAM data sheet and you read it and you design your memory controller to obey those latencies. That's the specification, basically. It really doesn't reflect the true DRAM device latency, right? This is very similar to if you get a processor. Intel, for example, says the processor operates at 4 gigahertz. This doesn't mean that it cannot operate at 5 gigahertz, right? Under the right conditions, you can make it operate at 5 gigahertz and you get no errors. But of course, the key is under the right conditions, right? And a lot of gamers actually do that. They overclock their processors so that they can get much higher performance out of their graphics, right? It's essentially the same phenomenon. You have margin that's included in the clock cycle time in the chips, and that margin is there for many, many reasons. One reason could be aging, for example. Over time, if you use the processor 5 years, maybe the latencies increase and you want to ensure that the processor still works, so you add some margin into your clock cycle, you increase your clock cycle, even though you know that it operates at this point in time much faster. Right? If you get rid of that margin, the probability of getting errors increases, of course, but if you know what you're doing, if you're getting rid of that margin in a methodical way where you really understand that margin is really not necessary for reliable operation, then you can actually overclock your chips to operate much faster. It's the same thing basically over here. Here, somebody specifies a latency in DRAM standards, and they guarantee operation at that latencies. But this is not the true DRAM device latency because there are a lot of factors that went into putting that latency parameter, let's say the activation latency parameter, into the DRAM standard. People said, okay, I want to add 40% guard band or margin to this latency because I don't know if it will really operate 5 years down the road if I don't add that margin. Right? That's the idea. Or I don't know, basically they also put that latency based on worst case conditions. At 85 degrees Celsius, I don't have a lot of charge, and I want this chip to operate with the same latency parameters at 85 degrees Celsius as it operates at 55 degrees Celsius. So I'm going to determine my latency parameters for operation at 85 degrees Celsius. Right? That leads to a lot of margin, basically, at 55 degrees Celsius. Okay. Basically, you have imperfect manufacturing process that leads to latency variation, and you get latency variation across DRAM chips. It's called manufacturing variation. And inside a DRAM chip, you also get latency variation. And basically, the DRAM manufacturers choose the standard latency somewhere over here so that they can maximize the yield. And also, they can have enough margin for operation so they don't get errors, right? Make sense? So that's why you have very high standard latencies. This chip over here is actually very fast, as you can see, but memory controllers are designed to use standard latency for all chips. So it doesn't matter. You basically pay the penalty of the standard latency, and there's a huge margin, as you can see, for this chip over here. Of course, this is pictorial. We'll see some real results soon. Okay. So what caused the long memory latency in this case is basically now we have conservative timing margins. We add all of this guard band. And this is actually not so good because timing parameters are set to cover the worst case. Worst case temperatures is one of them. Basically, the DRAM is promised to operate correctly at 85 degrees Celsius, but in common case you don't operate DRAM at 85 degrees Celsius, and this leads to significant margin in the common case. But you need to have ensure operation at worst case to enable a wide range of operation conditions. And if you have a single set of timing parameters that you dictate in the data sheets, you cannot really distinguish between two different temperature values clearly. And we're going to fix that, right? That's why I call this a fixed latency mindset. Basically, you have a fixed latency mindset. There's only a single set of latency parameters that's designed for the worst case. And there's also worst case devices. Basically, worst case devices are devices, basically DRAM cell with the smallest charge across any acceptable device dictates the latency. And if you have less charge, you have higher latencies because it takes a long time to sense the cell, to amplify the charge, and to read the cell. Basically, all of the operations become slower when you have less charge in a DRAM cell. And we will see why there's less charge in a DRAM cell in a little bit. Of course, this happens because there's process variation, and if you want to maximize the yield, you want to ensure that all of the devices, basically pretty much all of the devices, are acceptable. And if you choose a high enough latency, all of the devices become acceptable in the field. Okay, on top of this there's aging as well, which is not written over here, right? And this leads to large timing margins for the common case. Now let's understand and exploit this variation in DRAM latency. Now we know the basic reasons why that timing variation exists. But basically, it all boils down to the fact that DRAM stores data as charged. If you remember, there's a DRAM cell over here, there's a sense amplifier, and there are three steps of charge movement. You basically activate a row, which brings the data into the sense amplifiers, and that starts sensing at that point in time. That's the sensing procedure. Once sensing is complete, sense amplifiers start driving the charge, amplified charge, back into the cells. It's called restoration of the cell. And once you do the reading and all of that stuff, you need to pre-charge the array. And we've already discussed about the pre-charge. You have a pre-charge logic over here that sets the charge over here to, or voltage over here to VDD over 2, right? And these are the three steps of charge movement that you have. I didn't talk about the reading over here because reading doesn't happen in the subarray. Reading happens from the sense amplifier to outside somewhere, but that's also charge based. Okay, now let's go into a little bit more detail. This is the circuit simulation, if you will, as to what happens between a cell and a single sense amplifier. You have this charged cell. Initially, the sense amplifier is VDD over 2. It's pre-charged. And let's take a look at what happens when you send commands to DRAM. So initially it's charged. Sense amplifier is over here, VDD over 2. And we activate the cell. Activation starts sensing. The cell shares charge with the bit line. And this is what happens. Cell loses charge. And sense amplifier gains a little bit of charge, and soon after that sense amplifier kicks in, it gets activated, and it starts driving the charge up to the high value, which means that it restores the charge it sensed. Right. That's what's happening at the voltage level or charge level over here, as you can see. So in theory, this is the place where you should be able to access the cell reliably, right? Actually, it's a little bit earlier, but this picture shows that it's at the 100% point over here. And you can see that this is this value of charge means it's data 1. This value of charge means it's data 0. There's some encoding, and there's some noise margin over here that you shouldn't be at, basically. But in practice, people add some guard band over here. That's the timing margin. So in practice, memory controllers need to wait for this long because that's what the data sheet specifies. The question is, can we actually get rid of this timing margin over here? Right. So the question is, why do you need the extra timing margin? And let's take a look at these two things in a little bit more detail. We've already discussed at the high level, but at the low level, DRAM cells are not equal, basically, and this leads to extra timing margin for a cell that can store a large amount of charge. We're going to talk about temperature later. So what does it mean to not be equal? So if you have same size, you have same charge and same latency, right? That's homogeneous, but real life is very heterogeneous. So you have different size cells, which leads to different amounts of charge you can store, which means that you have different levels of reliable access latency. And if you have large variation in cell size over here, you have large variation in charge and large variation in access latency in the end, right? Now, of course, in this case, we say cell size, but what is cell size exactly? It's not just the cell size itself. So if you go into a little bit lower level, if you look at a DRAM cell, it has this capacitor. And actually, this is actually what it really looks like. It's much worse, actually. People etch these capacitors inside the devices, and the length or the height of this capacitor, I believe, is right now about more than 90x the width of this area. So you're really going 3D to really etch the capacitor inside, right? And this is one of the scaling limitations. How deep are you going to go, right? Are you going to go 1000x compared to the width over here? Okay, that way you can actually put a lot of capacitors side by side, because this is not as big of a limiter as you can see, right? It's really how deep you can go when you etch this. Okay, but you have the capacitor, you have the contact with the access transistor, and then you have the bit line. And all of these actually lead to latency effects. Meaning whenever you need to access, what happens is you connect the capacitor to the bit line, right, as we've discussed. Right? So cell capacitance is a problem. This could be large or small. That leads to different latencies. Contact resistance over here determines your latency also. And this transistor performance also determines your latency. So it's a complicated equation in the end. It's not just the size of the cell. Size of the cell is really part of it, right? This capacitor may have different sizes, this contact resistance may vary, and this access transistor performance may also vary. Bitline also varies, actually. We will see that later on. So I call this a small cell, means that small cell is weak in all aspects over here. Meaning that it has to be accessed with high latency because charge movement is slow, and it also stores small charge. You have small cell capacitance, high contact resistance, and slow access transistor. That's really the worst case, basically. All of these parameters are worse. That means that you need to wait for a long time to sense the data from the cell. And that leads to the high access latency. So that's hopefully obvious by now, right? Temperature dependence. Basically, DRAM leak, you know that DRAM leaks more charge at higher temperature. And this leads to extra margin for cells that operate at low temperature, right? Because at low temperature you have a lot of charge, which means that you have a lot of drive. In theory, as well as in practice, you can access the cells much faster. Right? And this is pictorially shown this way. This room temperature, this hot temperature. At hot temperature you have large leakage. And if you set your timing parameters for operation at hot temperature, in room temperature you don't need that much margin, right? Okay, I think we already discussed this. So you have large variation access latency. And the key observation is that DRAM timing parameters are dictated by the worst case, the smallest cell with the smallest charge in all DRAM products and operating at the highest temperature. And both of these compound each other. As a result, you get large timing margin for the common case. And this paper over here, adaptive latency DRAM, examines that timing margin. There's a lot of detail in the paper that I'm not going to talk about, but I'll give you the key idea. Yes?
How do you usually find the smallest cell? Looking for
Yeah. So you don't, in what I'm going to describe, our goal will not be to find the smallest cell, but our goal is to profile the DRAM to figure out what latency you can operate things at, yes. If you really want to try to find the smallest cell, it's going to be a mess, basically. Because it's not just the smallest, it's also the performance of the transistor and all of that, right? That's a good question. Our goal will not be that, basically. Yeah. Yes?
You say the capacitors are very thin and small.
Mm-hmm. Exactly.
Could you, for every other row, have the capacitor go the other direction?
Mm-hmm.
So you have a larger gap between capacitors and avoid row hammer?
I see, that's interesting. The row hammer is not exactly caused that way, actually. It's caused by some charge paths. The other direction meaning...
So you have one going like this, and then the next row they all go like this, and then...
I see. Yeah, you don't have that much freedom in terms of etching, basically, when you're fabricating. Yeah, unfortunately. But we can discuss that maybe later. Yeah, I don't think it all aligns the same way when you're really etching. Okay, hold that thought though. I'll need to think about this a little bit more. I don't think it will solve the row hammer problem though. Okay, so basically the key idea over here is essentially what I just discussed. Observe that there's timing that's different for the common case and optimize DRAM timing for the common case. to get rid of the margins as much as possible. Optimize for the current temperature, current DRAM module. Basically, we're going to exploit variation across temperature as well as across DRAM chips. So why would this reduce latency? As we discussed, in the common case, low temperature, strong cell, you can store much more charge, and more charge in a DRAM cell leads to faster sensing, charge restoration, and pre-charging. As a result, it leads to faster access. That's true for refresh, read, and write as well. But this paper examines these three over here. So I think I've already said this basically. Extra charge means reduced latency. You get lower sensing latency because you can sense cells with extra charge faster. You don't need to fully restore cells with extra charge actually. That leads to lower restoration latency. And you don't need to fully pre-charge bit lines for cells with extra charge. That leads to lower pre-charge latency. I can read the paper for more detail. Clearly, if you really want to do this right, you really need to examine real DRAM chips, right? All of the simulations point to that, but if you really want to figure out how much you can reduce latency in real life, you build this infrastructure that we already talked about, and you basically test DRAM chips. And you know that you can actually use this infrastructure for many studies. People have done that. And that's what exactly we did. Clearly, faster sensing happens because you have more charge and you have strong charge flow. And it turns out you can reduce the activation latency by 17% on average across 115 DIMMs that are characterized in this work, and you get no errors. And that points to the fact that there's a lot of margin, as you can see. Of course, there's a variation. 17% is average, right? Different chips have different values for that. Okay, we already discussed that. The second one, and this is operating at low temperature basically. And the second one is reducing the restoration time. You have less leakage, you have extra charge, which means that you don't need to fully restore charge and you can correctly operate. Because the timing parameters are designed for 85 degrees Celsius, right? If you don't fully restore charge at low temperature, you will still get the same amount of charge that you would have gotten at 85 degrees Celsius by fully restoring the charge. Right? That's the idea basically. Because you added just too much margin to operate at low temperature. And you can see that the read latencies and write latencies can actually be reduced significantly, even more significantly than what I just showed earlier, without getting any errors. Okay, so clearly this leads to restore time reduction. There's more in the paper that I'm not going to talk about. Yes?
Generally, when the chip is fabricated, so we do a billing so that we can determine like what is the speed grid we decide like
yes.
That. So is not it the same case for the DRAM chips also?
It's in DRAM chips you do that for frequency but not for latency. Okay. So latency binning doesn't exist in DRAM. But you could think about this as latency binning, yes. A way of doing latency binning. Yeah. Okay, so the key idea over here is to optimize the DRAM timing parameters online. There are two components. Somebody, in this case DRAM manufacturer we assume, provides multiple sets of reliable DRAM timing parameters at different temperatures for each DIMM. Basically, as opposed to having a single set of timing parameters, you have another set at 55 degrees Celsius, let's say. If you're operating below 55 degrees Celsius, you use the lower latency timing parameters. And you provide it for each DIMM separately. And you can store this inside the DIMM, and then you can read it, and memory controller can figure it out just like it happens today. And the system monitors the DRAM temperature and uses the appropriate DRAM timing parameters. So it's a very simple idea in the end. And today, DRAM temperature monitoring exists in all of the DRAM chips. But today, this doesn't exist. Basically, somebody needs to provide the reliable DRAM timing parameters. So assuming that you do that, let's take a look at what the results will be. Actually, one of the other questions is, what is the DRAM temperature that you usually operate at? And it turns out DRAM standard is optimized for very high temperatures, but you don't normally operate DRAM at very hot temperatures. In fact, you don't want to operate DRAM at very hot temperatures. Unless you have very heavy 3D stacking, you don't go into very high temperatures basically. And actually there are a lot of works that show that DRAM temperature is low. And there are a lot of works that want to maintain the low DRAM temperature for reliable operation as well. Right? So low temperature is a good thing also. And it turns out in the common case, DRAM operates at low temperatures. So let's summarize the latency reduction for 115 DIMMs. That's almost 1,000 chips basically. It turns out that if you're operating at 55 degrees Celsius, you can reduce the read latency and write latency significantly. 30%, 55%. So this shows you that there's a huge margin, right? Most of DRAM latency in the case of writes is unnecessary. And each timing parameter is analyzed in the paper. The paper has actually a lot of results for each DRAM chip. Now let's take a look at how much benefit you would get if you actually do this, use this idea on a real system. And this is essentially what we did. On a real system, you cannot dynamically change the latencies during operation, at least on most systems that are available to general purpose users, let's say. But you can statically change latencies on some systems. So this is an AMD system, and some of the memory latency parameters in the BIOS, you can set them to be lower or higher. And actually, if you're a gamer, you should be doing this probably. How many of you are hardcore gamers? I think I asked this question before. There are no hardcore gamers here. Okay. Basically, you reduce the latencies. But of course, we want to reduce the latencies intelligently. If you reduce the latencies too much, you can get crashes and errors. Basically, what we do is we test the DRAM chips, figure out the reliable operation latencies at 55 degrees Celsius, and set the latencies to those values that lead to reliable operation. Now, if you do that, and if you run a bunch of workloads, these are the results that you would get. These are some benchmarks. They're single-core workloads, so they're more latency-bound, single-threaded. And the average improvement we get is about 6.7% for memory-intensive workload, which is actually significant because you're not changing a lot in the system. You can almost do it in real systems, but we're not doing it dynamically, as you can see over here. It's static. Of course, you need to ensure that the system doesn't go over 55 degrees Celsius in this case, right? And in our system, you don't need to do anything to make sure that it doesn't go over 55 degrees Celsius. Most systems don't go over go to very high temperatures. Okay, if you actually have, and that's the average across 35 workloads in the paper, you can read the paper for more detail. So basically, you can get significant performance improvements on a real system. And performance improvements actually increase if you have multiple applications running in the system. This is a scenario where we have multiple copies of these I think we have 4 copies of each benchmark running on 4 cores at the same time. You can see that there's a significant, even more performance improvement that you get. It's about 14% across the intensive workloads, memory-intensive workloads. And this shows that when you have multiple workloads that are accessing memory at the same time, latency becomes a bigger issue. Because you're bandwidth limited, and you get a lot more collisions in the banks, and your bank conflicts increase, and your queuing latencies increase as a result, and latency becomes a bigger bottleneck, so your performance improves even more when you have more workloads accessing memory. Okay, and there's a lot more analysis in the paper, but I'll let you read the paper. I'll give you one more data point here. This is not a very full analysis, but there's very initial analysis that also shows that if you reduce the latencies, it's good for energy as well. Because when you reduce the latencies, you're really driving the circuits for a much shorter time, and that leads to a reduction in energy. And I believe, as we discussed yesterday, reducing latency is a good thing, not just for performance, but also for energy. Yes?
If you want high performance, aren't you going to push the system to get used to that, and then you would go above 55 degrees anyways?
Uh-huh.
So, like, what is the use of only getting performance improvement at lower temperatures?
Oh, I see. Because most systems operate at low temperatures to begin with.
Yeah, but
so you're wasting a lot of performance.
You don't push the system to its maximum. Right now, you're kind of raising the bar for what the system will do. When you go there, you will end up in a higher temperature.
I see. So that is true, although if you have a system like this, DRAM usually doesn't have very high temperatures because most of it is really not accessed. It's very hard to get it to very high temperatures. That's what we're exploiting here. Unless you're really sitting out in the heat or heating something, then you don't go into very high temperatures. Now, if you actually start doing computation in memory, that's a different thing. Now you may actually be heating the DRAM itself, and some of these ideas, like this particular idea, becomes less effective, at least from the temperature perspective. But we have some other solutions to that will come soon. Does that make sense?
Yeah.
Yeah. Okay, so basically you pointed out the downside of the idea. If the system is operating at high temperature, you're not saving as much, which is true. You're exploiting still the latency variation across chips, though. That will remain there. But you're not exploiting latency variation across temperatures in that case. Okay, so let's talk about the advantages and disadvantages. This is a very simple mechanism to reduce latency. You get significant system performance and energy benefits, and benefits are higher at low temperature, clearly, although benefits are still there at high temperature as well, but not as much. And it's low cost and low complexity, basically. You need to change the memory controller to keep track of which latencies to use. And clearly you can generalize the idea, not just have two sets of parameters, but multiple sets of parameters. Right? You can, at 70 degrees Celsius, you may have another set of parameters. Of course, there's a disadvantage. Somehow, somebody needs to determine the reliable operating latencies for different temperatures and different temps, which means that this is higher testing cost rate. And I think clearly this may increase the DRAM prices slightly. I don't believe it's a lot of overhead, but we have good motivation to actually do this essentially dynamically. But this may not be that difficult for low temperatures also, right? Because you're already testing for high temperatures. You might actually add another step for testing for low temperatures. Okay, so if you're interested, there's a lot more over here. Any questions? Yeah, some good questions. Okay, so now we're going to talk more, basically. So adaptive latency DRAM exploits latency variation across time, different temperatures. I think of this as time, and across different chips. The question is there also latency variation within a chip? And we're going to answer that question, and the answer will be yes, because I've already given you the answer. Essentially across different parts of a chip. Now let's take a look at the next work that talks about this. First of all, let me give you the latency variation across different chips first. This is not going to look at the same chip. This is basically looking at 240 chips, and this is reducing the activation latency. Standard is 13.1 nanoseconds for this particular DRAM standard that we examined. And let's take a look at what happens to the bit error rate that you get from DRAM as you keep reducing. Presumably you should be at zero over here, right? I think 0 is over here. 10 to the 0 means it's a very high bit error rate. Actually, it's 100%. Okay, so basically at some temperature, I don't remember what temperature, but it's very close to 55 degrees Celsius, I think, over here. As you reduce the DRAM latency to this area, 7.5 nanoseconds, you don't get any errors. This is activation latency, because there is a significant margin at temperature for all of the chips. Now let's take a look at what happens at 7.5 nanoseconds. This is the distribution of the bit error rate that you get across the 240 chips that are tested. You can see that there's a huge distribution, right? Some of them actually have very low error rates over here. Some of them have relatively high error rates. 10 to the minus 2 is 1 out of 100 bits get errors. And these are the quartiles, as you can see. So clearly you have very different characteristics across DIMMs, but you may be able to tolerate some of these error rates as well, right? Especially if your application is tolerant. You can somehow make use of that, and we're going to talk about that later on. A lot of the machine learning applications could tolerate these error rates. These error rates are maybe a little bit high to tolerate. But of course, if you keep pushing the latency even more to 5 nanoseconds over here, now your error rates start increasing a lot, right? And if you keep pushing them even more, 2.5 nanoseconds, you're almost there. There are some cells that are getting errors. There are some chips where all of the cells are faulty, right? So clearly, you don't want to push things over here, but you want to identify. If you want to operate reliably, you want to identify the boundary over here. Clearly, at 10 nanoseconds, there are no errors, so you can reduce the latency by about 30% over here. But as you go to 7.5 nanoseconds, maybe you can still tolerate these errors, assuming that your application is tolerant. That's the idea. But we're not going to go into the application tolerance at this point. Okay, I think I already said this. So we already knew this, but I wanted to pictorialize for you some of the things that you can see visually. Now let's take a look at the variation inside a chip. So this is one example of the variation that you get inside a chip. You can think of this as rows and cache lines. This is kind of a single bank. And the way to read this graph is we reduce the activation latency to 7.5 nanoseconds from 13 nanoseconds. And we measure the bit error probability of a given cache line having more than or at least one bit error. And this is a density plot, basically. You can see. So clearly, a lot of your chip is strong, even at 7.5 nanoseconds. Right? There are only some parts of the chip that are not so strong. And if you can somehow identify this, maybe you can exploit this variation. If you're accessing this cache line over here, you can access it with 7.5 nanoseconds. If you're accessing this cache line over here, you access it with 13 nanoseconds, or whatever it is where you're not whatever the latency value you're not getting errors at. Right? That's the idea, basically. This way you can exploit the spatial variation that you get. So this happens again because of manufacturing variation. For some reason, these bit lines were not very strong, for example. We won't get into that. The paper has a lot of detail on that. But basically, this is the takeaway. Activation errors are concentrated on certain columns of cell, and you can actually, if you're not accessing them, then you can actually get significant performance improvements. So this is observation. Basically, timing errors, when you reduce the latency, or slow DRAM cells are concentrated on certain regions. And the idea is very simple once you realize that. You create a software transparent design that reduces latency. You could potentially expose this to software also, but we don't want to go into that complexity at this point. You divide the memory regions into regions of different latencies, and the memory controller uses lower latency for regions without slow cells and higher latency for other regions. Clearly, this complicates the memory controller because it needs to store which regions can be accessed with which latency, right? But you will see that the performance improvements are even more significant. So let's take a look at some real chips. I'm going to show you, I think, 3 DIMMs, real DIMMs that are tested. And we're going to look at the activation latency variation and the pre-charge latency variation. And if you look at the baseline, the standard says activation latency should be 13 nanoseconds for all of the cells. Now if you look at this DIMM, 12% of the cells can be accessed with 7.5 nanoseconds, and 88% can be accessed with 10 nanoseconds, as you can see. This is an even stronger DIMM. 99% of the cells can be accessed with 7.5 nanoseconds. Only 1% of the cells need to be accessed with 10 nanoseconds. And none of the cells require 13 nanoseconds at this temperature. And that's true for TRP also, as you can see. And the DIMM, clearly the latencies are correlated over here. The pictures are very similar, as you can see. Now, if you expose this to the memory controller, the memory controller accesses 99% of these cells with low latency and 1% of these cells with slightly higher latency, still less than the baseline latency. And of course, the upper bound in this case is all of the cells can be accessed at 7.5 nanoseconds, right? And we're going to compare to this upper bound. This is going to get close to the upper bound. Clearly, it's going to get far away from the upper bound. So now, of course, now you've figured out this data from real DRAM chips using infrastructure, and you want to model what you can do. You use simulation, right? Because you cannot modify the memory controller. Well, you could potentially, but that's a lot of work in this case. But you can use simulation to get an idea of what would the benefits be if you actually exploited this spatial latency variation that you have inside a chip. And this is the baseline, average across 40 workloads. This is normalized performance you get. If you use this DIMM1, remember it had 12% of the cells that could be accessed at 7.5 nanoseconds, remaining cells can be accessed at 10 nanoseconds, you get significant performance improvement. If you actually use the next DIMM, you get even more performance improvement. And the next DIMM, where you can access 99% of the cells at 7.5 nanoseconds, you get even more performance improvement. So simulation kind of validates your expectation, but it also puts some numbers over here. And also, it's a good way of validating your simulation is to figure out what happens when you have ideal. In this case, ideal, all of the cells can be accessed at 7.5 nanoseconds, and that gets very close to this one, as you can see, as expected, right? So clearly, exploiting the variation inside a single DRAM chip leads to significant performance improvements, even more so than exploiting the variation that we discussed earlier. Okay. Any questions? Is this fun? Okay. So it's amazing what you can do, right? Once you really understand what's going on underneath. Okay, clearly this has advantages and disadvantages. It reduces latency significantly because it exploits within chip latency variation now. But now there's even higher testing cost, right? Somehow you need to determine the reliable operating latencies for different parts of a chip. And that leads to higher testing cost. And also you need to complicate the controller a little bit. This is not necessarily, it's not as true in the adaptive latency DRAM. Here you really need to store which parts of a DRAM chip need to be accessed with which latencies, right? And you need a mapping structure for that, basically. That maps a given row or a given part of a DRAM chip to a particular latency parameter. Okay, so that's not going to be as easy. It's going to be a little bit more costly, clearly. But if you want to get the performance results, that's what you need to do. Okay, this is actually, this paper is going to put it all together. I'm not going to go into a lot of detail over here. It has a nice name called Solar DRAM. It basically puts a lot of the ideas together, and it also examines some new things. So basically it looks at spatial distribution of the DRAM cells. It turns out you can reverse engineer what your DRAM chip looks like by reducing the latencies and looking at the error patterns. This is one example. Basically, this is these are DRAM rows over here. These are DRAM columns. And if you aggressively reduce the latency, you get failure patterns that look like this. Black means, the darker black means you get more failures, basically. White means you don't get failures. But you can clearly see a boundary over here, right? And it turns out that's the subarray boundary in the DRAM chip. So clearly this subarray is different from this subarray because the bit lines are not connected to each other. And as a result, you get different failure patterns across subarrays. And if you actually do this for your entire DRAM chip, you can get a picture of your DRAM chip that shows the failure patterns, and you can reverse engineer where the subarrays are, and you can reverse engineer even more in terms of the structure of your DRAM. Basically, you don't need to take a picture of your DRAM chip. You can actually have a memory controller where you reduce the latencies, and you can figure out what your DRAM chip looks like internally. Yes?
Doesn't that solve the problem of not knowing where adjacent rows are for the row hammer solution?
So that's a good question. Assuming that you get errors differently across different rows, yes. Exactly. I believe there's work to be done over there to actually figure that out exactly. Now, we have not done it completely, but you're absolutely right. Going toward this direction can aid that. Okay, so this is one thing that I want to share. Basically, you can reverse engineer a lot about your chip if you induce errors in your chip. That's a very good way of reverse engineering your chip. Okay, I already said that. Basically, there's another observation clearly. Activation failures are highly constrained to local bit lines also. And different subarrays have different properties in terms of their bit lines. So there's also another question that we wanted to answer, and this is also important. Assume that you fixed your latency of a bit line. How long is that latency valid? Does it change over time, right? Basically, if you remember the retention time is subject to change because of the variable retention time effects, right? Latency doesn't seem to have that sort of effect as much, and this basically validates it. This is a failure probability of a cell at time t1, and this is the failure probability of the same cell at time t2. You can see that there is a very strong correlation. Basically, if the failure probabilities wouldn't change, you should have a curve x equals y over here. Now it's a bit noisy over here, but the correlation is really strong. And of course, you should ask what is time 1 and time 2. I believe things were tested for more than 30 days or so. So this answers the question, if you actually profile your DRAM chip and figure out the latencies of different cells, how long will that profile remain valid? And the answer is a weak bit line is likely to remain weak, and a strong bit line is likely to remain strong over time. But of course, we didn't do the study for 5 years, so it's hard to do this study for 5 years. If you know a way of doing this, actually, I'd be very interested in learning. You can, for example, heat your DRAM chip and put it under extreme conditions and try to accelerate the aging, but it's not, I think, the same thing as using it for 5 years. But at least in the short term, there's not much variation in terms of the latency of a DRAM cell. Okay. Which means that you can rely on a static profile of weak bit lines to determine whether an access will cause failures. Somehow statically profiled. I don't think this is actually exactly true. I think you still need to dynamically profile over time, but your dynamic profile remains valid for a good enough of time. Okay. So I'm going to skip a bunch of these, I think. You can read the paper. Basically, it turns out you can actually play a lot of tricks and reduce the write latencies even more significantly. I'm not going to talk about that. If you're interested, you can read the paper. And I think I'm going to skip this one also. Basically, the paper has a lot of interesting ideas. So once you actually know your DRAM chip, you can actually reduce the latency even more. Maybe there will be a lecture about this later on, but I'm not going to talk about this one. So any questions? I know I didn't talk about all of those, but I like examining this time variation of latency. I think there needs to be more studies in terms of aging in these chips. One of the key questions is how bad does latency or refresh or errors vary when your chips age? And I don't think there are very good studies that have shown this. And the main reason is really it's a difficult study to do, right? In a controlled manner. You can do the study in the large scale like we've done with Facebook that I mentioned earlier, and you see some aging effects over there, no question about that. But you cannot control many of the factors over there, because over the course of 5 years in data center operation, who knows what kind of effects have happened, right? You cannot control all of those effects. In the end, it's a correlational study. Okay. Any more questions? So let's try to answer this question a little bit now. Why is there a spatial latency variation within a chip? I think we already talked about this, so it's going to be relatively obvious to those of you who asked the questions also. Basically, there's clearly some design-induced variation inside a chip. And this is really dictated by how close a cell is to the sensing structures. Right? So you have two kinds of sensing or driving structures, sense amplifiers over here and the word line drivers over here. When you decode the row, you activate the word line, right? And how close a cell is to those structures dictates its access latency. So you have a variation across the row. If you're closer to the sense amplifier, you get charged relatively quickly, so it's fast. If you're farther away from the sense amplifier, you're slower. And you have variation across the column. If you're closer to the word line driver, you get activated more quickly. If you're farther, you get activated more slowly. So if you look at this picture, assuming this picture is correct, you have an inherently fast region in DRAM, and you have an inherently slow region in a subarray. Again, across different subarrays, it looks the same, but you may have variations across different subarrays. But the picture should look the same over here. So this, basically you have this systematic variation in cell access times, and this is really caused by the physical organization of memory. And I think this variation also exists in any type of memory, not just DRAM. As long as you have some sensing structures, and as long as you have variation in terms of proximity to those sensing structures, you will have the same effect. In DRAM, it's exacerbated because in charge-based memory, sensing structures are extremely important, right? The latency is dominated by how fast you can do that charge movement. Whereas in some other technologies that we will discuss, latencies are a little bit different. It's not about charge movement, it's something else. It's about detecting the resistance, for example. Okay, so if you have this picture, then what can you do with it, right? Basically, the key idea is, if you somehow know this inherently slow region, then you can test only that region, and that gives you the lowest reliable access latency to access DRAM with, right? You don't need to test this region, because if you know that this region can be accessed reliably, you can assume that this region can also be accessed reliably, right? Assuming the systematic variation holds. And we will see data that it does actually hold. So now you see that you can reduce the profiling cost, right? The question is, how can you actually find out the lowest latency you can access a DRAM subarray with? Somehow figure out this region and dynamically test that region once in a while, every 30 days, let's say. That way you can actually reduce your testing costs as much as possible, because you're not testing the entire chip, and you can adapt to dynamic changes in latency, whatever they may be. That's the key idea, basically. Exploit the systematic variation over here to minimize the profiling cost. And this is called design-induced variation-aware profiling. There's an inherently slow region, and profile only those slow regions to determine the minimum latency. So memory controller, once in a while, what does profiling mean? Once in a while, memory controller starts testing this region. It sets the latency to a value. It sees if it's getting errors. Of course, it does it for different data patterns, ... It basically builds some confidence that this is the reliable latency that you can access with. And if it starts getting errors, it says, okay, I'm not going to use that latency. I'm going to use the latency where I'm not getting errors, the minimum latency where I'm not getting errors. That's the idea. Now, of course, this is good because you're testing only a very, very small region, and it's dynamic and low cost because of it. But of course, that's not the full picture, right? As we discussed earlier, it's not just systematic variation. Actually, I'm just introducing systematic variation. You've discussed it, you figured it out earlier, some of you. But we really talked about process variation also. And it turns out there are a bunch of DRAM cells over here that will not work if you do what I just said, because they don't obey the systematic variation. They have this random process variation, and they're slow because of that randomness in the process. Now, how do you take that into account? Now, remember the fundamental principles. You can figure out the lowest latency if you have systematic variation with the technique that I said. Now, if you have these random errors that you get when you reduce the latency, how do you fix them? Basically, you can correct the errors, right? That's the idea over here. These are two different kinds of failure modes when you reduce the latency. These are inherently slow ones. They're inherently slow because of design-induced variation. They're localized errors. And you can correct these errors, if you will, by ensuring that you don't get those errors, by operating at the minimum reliable latency. And if you get errors in other chips, other cells that do not follow the systematic variation that happen because of process variation, these are random errors, and you used error correcting codes to correct them. And these turned out to be very randomly distributed across a DRAM chip. And because they're randomly distributed, you get one cell within a word, within an ECC word. So you can actually use relatively weak error correcting codes that you have today. Of course, if you keep pushing the latency much lower, you need to increase the error correcting code strength, clearly, right? If you start getting more cells that are randomly failing because of this. And that's the key idea basically here. You combine online profiling to figure out the slow regions and correct the errors that are happening because of random variation using error correcting codes. And we know that existing DRAM chips already have error correcting codes. This is one way of actually taking advantage of the internal error correcting codes inside the DRAM chips. And this reliably reduces the DRAM latency if you actually, of course, set your latencies to an appropriate level, as I discussed, right? Clearly, this also opens up a trade-off space now, right? Now you can reduce the latencies even more aggressively if you increase the error correcting codes. That trade-off we didn't discuss as much. There's a performance reliability trade-off. Clearly, we did discuss that one, but we didn't discuss it from the perspective of error correcting codes, right? So now your design space becomes even more interesting. Right? Okay, so let's take a look at results from real chips again. This is testing. We tested a bunch of chips again. I don't remember how many, but this is adaptive latency DRAM that you've seen. At low temperatures, it reduced the read latency significantly, as you can see. At high temperatures, it's not as effective, but it's still reasonably effective because it exploits the inter-chip variation. If you use the STIVA profiling, you actually reduce the latencies even more because you're more targeted. You're really exploiting the systematic variation. And also, you're using error correcting codes actually enable slightly more reduction in latency. Adaptive latency DRAM does not rely on error correcting codes, right? Here you pay the cost of error correcting codes. But it turns out you can actually reduce the latencies even at high temperatures this way, because you're not reliant on temperature as much. Right? You're really exploiting the systematic variation, and on top of that, error correcting codes makes things a lot better. And also the paper discusses once you have these error correcting codes, you can actually take advantage of, you can actually redesign your error correcting code slightly to improve your latency reductions better. But I'm not going to talk about that. Basically, you can pick the words that go into which what you're protecting, because you know that some bit lines are stronger and some bit lines are weaker. So you target your error correcting code so that you can protect your weaker bit lines. Right? That's the idea. If you know the underlying structure of where their errors are coming from, you can change your error correcting codes also to take advantage of that. And these are read latencies. Write latencies are relatively similar, as you can see. The downside of adaptive latency DRAM, as you pointed out, was actually at high temperatures, you don't reduce the latencies as much, but now we got rid of that downside. At least mostly. There's still a slight thing that you see over here, and that's because the DRAM is still less reliable at high temperatures, right? Okay. So clearly now we've complicated things. But this also, there's another advantage over here that I didn't emphasize. But this does dynamic profiling, right? Adaptive latency DRAM relies on a static profile given by someone. So in a sense, this is more robust. So if there are aging effects, here you cannot adapt to them, and you need to add more margin. And these are optimistic results actually for adaptive latency DRAM, because if you really want to operate the chips out in the field for 10 years, you need to add some margin. But here, you can discover the latencies dynamically over the course of 10 years by continuous testing online, because you reduce the testing cost significantly. Right? So in a sense, this is a lot more robust than this one. I don't believe this idea actually works. It works if you add enough margin, clearly, but the benefits will be lower than this. Okay, that's the beauty of doing dynamic optimization while the system is running, as opposed to relying on some timing parameter that someone else provided. Okay, so let's talk about the advantage and disadvantage of this. Clearly, I think the big advantage is this double plus. It automatically finds out the lowest reliable operating latency at system runtime. which means that now your production time testing cost is reduced. Of course, you need to do testing of your profiling mechanism, like memory control needs to be operating correctly, but there's some testing cost on that. But you don't need to figure out the latency parameters correctly for every single DRAM cell during production time. And it reduces latency more than prior methods. With ECC, error correcting codes definitely boosts the latency reduction, because prior mechanisms that get errors without error correcting codes, this mechanism can correct those errors. And it reduces latency at high temperatures as well. Of course, now the downside is you need to know these inherently slow regions. Right? The question is, how do you find out those inherently slow regions? One, basically, somebody needs to provide them to you. This is another reason why it's a good idea to have better communication between DRAM chips and the memory controller. We had another reason for the row hammer, for example, right? You want to know the physically adjacent rows. There are many, many of such reasons. Or you can reverse engineer, right? With the mechanism that we discussed. Actually, that's exactly what we did. If you read the paper that looks at this, we show the systematic variation with pictures, and we discover those inherently slow regions by reverse engineering, by testing. So you could actually do this. But I believe the better method is really having a protocol between DRAM and the memory controller, where the DRAM says, these are my inherently slow regions in my subarrays. Right? And then the memory controller dynamically profiles them. Okay, it also has another downside, which is it requires ECC, error correcting codes, right? But this is going to be there for many, many reasons, as we discussed. Now, this is one way of taking advantage of the error correcting codes. But of course, ECC is needed for multiple reasons when you scale the technology. Like variable retention time is one reason we discussed, right? Variable retention time errors can be corrected by ECC. If you use the same ECC to correct the latency errors, that may not be a good idea. Because if variable retention time happens at the same time a latency error happens for different cells, you may not be able to correct those errors now, right? So this is actually really a case for having more stronger error correcting codes inside the DRAM also. And I believe that's going to be inevitable also as you scale the technology down. You really need higher capability in terms of error correcting codes. Okay. Well, there's also this, but this is not as big, I think. Clearly, we need to do runtime profiling over here, and that imposes some overhead. And the key idea is to really minimize that overhead. If you profile the entire DRAM chip, this would be not sustainable, I think. If you profile only a very small region, then it's very sustainable. Okay. Okay, any other thoughts? And this is the paper that talks about it. There's a lot more data in the paper, and this is part of Don Kyok's PhD thesis. Okay, so let's see, how much time do we have? Do I want to go into the voltage? What do you think? Any questions? I guess I'll take some questions and we'll decide whether we want to go into the voltage. Now you can hammer me and ensure that we don't go into the voltage. That's one way of preventing going into the voltage. This will take some time, that's why I'm hesitating. Any thoughts? You've seen a lot of ideas. And I think all of these ideas came about because you wanted to break the mindset of fixed latency as well as how to design the DRAM microarchitecture. No thoughts? Was the Turkish delight too heavy? Was it good, by the way? Okay. Okay, maybe this is a good time to stop actually. We'll pick up on the different things related to this voltage, latency, reliability, because this will make things more complex, as you can see. So far we've been exploring the latency reliability relationship. Now we're going to add the voltage on top of that. But it's going to be very interesting because if you can reduce voltage, then you can actually improve energy efficiency as well, even more. But I think we're going to pick this up next time. So I guess for now, have a good weekend. I'll see you next week.